USA. Comprar o vender una propiedad es un paso que impacta su vida y la vida de su familia y sus seres queridos. De hecho, estudios demuestran que tener un grupo de agentes de bienes raíces con experiencia garantiza un mejor precio al momento de vender, comprar o alquilar una propiedad. Si quiere comprar o vender una propiedad, LMS Realty es su solución. Contamos con los recursos y la experiencia para agilizar su transacción con facilidad y alcanzar el mejor precio posible. Al mismo tiempo, LMS Group puede hacer evaluaciones de mercado y podemos proporcionar varias soluciones de financiamiento para encontrarle la casa de sus sueños. Además, LMS Realty puede proporcionar varias soluciones de financiamiento para que pueda tener su casa con un menor costo posible. Tome acción hoy mismo. LMS Realty es su solución ideal.
Broadcasting live from Houston, from the space city to the world. You are watching Now Media Television.
Just in case you hadn't already guessed, I'm a nerd. I'm a full-on read science fiction, go to cons and cosplay, wish I had time to learn Klingon nerd. This means that sometimes when I read science stories, I get excited at the possibilities the new discoveries offer novelists and showrunners. I really want to see the story about living on a planet locked so one side always faces the sun. I want to see the accurate disaster story where a civilization has to escape their world in the face of a magma plume causing mass extinctions. I want today's science in tomorrow's space operas. But only to a point. In today's episode, we have stories that had me thinking, this is how you get Cylons, and I do not want Cylons. And I may have actually stated, I think this is the plot to Snowpiercer, just before reading assurances that one team's science would not lead to Snowpiercer. There is a give and take between science and science fiction, where the ethics and cautionary tales of science taken too far can serve as a warning or inspiration to researchers. Star Trek did inspire many of today's medical devices, tablets, and flip phones. There is good. In this show, we'll go through more than 20 studies and observations, ranging from planetary climates to galaxy mergers. And we'll take a closer look at how artificial intelligence is being asked to play a role in every area of this research. And I'll ask, is this how we get Cylons? For now, I think the answer is no, but I'll leave it for you to decide. I'm your host, Dr. Pamela Gay, and I am here to put science in your brain. Last Sunday, I caught a couple headlines that caused me to go, nope, that cannot be real science. Both of them read along the lines of scientists consider using moon dust to cure climate change. And on Monday morning, I learned those headlines were actually pretty spot on and described an actual proposal published in the journal PLOS Climate. Written by Benjamin C. Bromley, Samir Khan, and Scott Kenyon, this paper titled Dust as a Solar Shield, considers the possibility of blasting dust from the moon toward the gravitational balancing spot between the Earth and the Sun. That gravitational sweet spot is called Lagrange 1, or L1, and it is where we tend to stick things like solar telescopes that allow us to predict space weather. In a 5 a.m., what if we tried conversation, many of us have speculated that putting some kind of a sun shield at L1 or otherwise finding some kind of space-based way to limit the sunlight hitting Earth might help us deal with climate change. But like most 5 a.m. ideas, this topic was generally set aside as something that couldn't survive the scrutiny of daylight. But with climate change research saying we can no longer prevent our planet's average temperature from increasing more than 1.5 degrees Celsius, some of those late-night ideas are starting to see serious consideration. In this paper, Bromley, Kahn, and Kenyon consider two scenarios. In the first, they place a theoretical large space station at L1. Due to L1's 1.5 million kilometer distance, any station we could build would do essentially nothing to block sunlight. If, however, the station could constantly spread dust, like an overly aggressive salt truck on an icy road, that dust could spread out to effectively decrease the light reaching Earth for a couple of days. Well, L1, like its partner L2, is a fairly stable place to put a spacecraft like Solar Dynamic Orbiter or JWST. It is not stable enough for dust to stay put when it is also getting blown about by solar winds affected by radiation or tugged by the regular motions of solar system objects. Since we don't have a perpetual dust machine, this idea isn't very practical. But the creativity of scientists doesn't tend to take "that's not practical" as an answer. And this brings us to destroying the moon. In an idea that I'm pretty sure would require an amendment to the 1967 Outer Space Treaty, this team went on to calculate if it would be possible to put dust fired from the moon onto the correct trajectory to get it to maintain a position between the Earth and the Sun, such that the dust would create a bit of shade for good old planet Earth before the dust dissipated. According to the team, quote, "The amount of dust required for a solar shield is large, comparable to the output of a big mining operation here on Earth," end quote. And that is doable. Messy, disfiguring, expensive, but doable. As Kenyon says, quote, "It is astounding that the Sun, Earth, and Moon are in just the right configuration to enable this kind of climate mitigation strategy," end quote. When I initially read the paper, my first thought was, this feels like how you get Snowpiercer, and I don't want to live in the universe of Snowpiercer. Amusingly, the researchers addressed this concern head-on, stating in a Harvard-Smithsonian press release, quote, "One of the biggest logistical challenges, replenishing dust streams every few days, also has an advantage. The sun's radiation naturally disperses the dust particles throughout the solar system, meaning the sun shield is temporary and particles do not fall onto Earth. The authors assure that their approach would not create a permanently cold, uninhabitable planet, as in the science fiction story Snowpiercer," end quote. I hope we find other ways to mitigate climate change before we have to do anything this intensive. But the option is there. And the rest of this week's news on climate change makes me reluctantly glad that folks are thinking so far outside the box. Our world is a planet, and this is your periodic reminder that Earth science is planetary science. Researchers who study glaciers here on Earth may also study ice interactions on worlds like Europa. And it is through our combined observations of science in every environment that we can fully understand this world and worlds beyond our solar system. Glaciers are one of the most powerful variables in Earth's history and its future. New research led by Robert Law looked at the structure of ice through the full thickness of glaciers in Greenland. These borehole measurements made it clear that our current simplified models can't adequately predict the kinds of ice found in varying thickness over the length of a glacier as it passes over complex landscapes. By adding more sophisticated ways of handling energy to new computer models, his team can replicate what is observed and see what is actually happening. They find that where moving glaciers collide with hills and other obstacles, pressures build in the ice and softer forms of ice, temperate ice, form. As Law describes it, quote, "Because of this hilly landscape, the ice can go from sliding across its base almost entirely to hardly sliding at all, over short distances of just a few kilometers. This directly influences the thermal structure." End quote. The temperate ice that forms contains water and allows material above it to more readily slide. Law goes on to explain that this temperate ice layer can act as a bridge between hills, facilitating the fast motion of the much colder ice directly above it. The melting of the Greenland ice sheet is the single largest contributor to global sea level rise, and these new models have so far been tested against observed data. Their next step will be using the models to refine predictions of ice movement and melting. While the melting of Greenland's ice sheet is an existential crisis like few others, its glaciers don't pose a day-to-day threat to very many people. Fulfilling that role on the global hazard map are the glaciers of Peru, India, Pakistan, and China. Fast-flowing glacial lake outburst floods occur when meltwater bursts from lakes and races down mountains and through valleys. These floods can burst dams, shatter bridges, and destroy hydroelectric facilities, and wipe out entire villages. In a new paper in Nature Communications, researchers led by Carolyn Taylor demonstrate that 15 million people live within 50 kilometers of a glacial lake, with 9.3 million of those people residing in the region of the high mountain Asia, which encompasses the Tibetan Plateau. While the Asian glaciers are reasonably well studied, the research team points out there is less understanding of glacial lakes in the Andes, and research is urgently needed. Ultimately, much of the meltwater from these glaciers will make its way to the sea. According to NASA, sea level along the U.S. coast could rise 12 inches by 2050, and a longer-term study by the National Oceanic and Atmospheric Administration predicts a total rise of 3.5 to 7 feet by the end of this century. This is within the lifetimes of today's young children. And a new study led by Ebru Kurezi that appears in Frontiers in Marine Science shows that these changes to our coastlines will devastate economies with a cost of roughly 3% of the global gross domestic product. The regions most affected, Asia, West Africa, and Egypt, are the ones least able to shoulder these costs. Wealthy nations can raise buildings, create coastal mitigation features, and otherwise architect their way out of the worst effects. As study co-author Ian Young explains, quote, "Developing nations will be devastated, both in terms of people impacted and their economies. If the money to mitigate this impact in developing countries is not found, communities will be forced into coastal retreat, and there will be significant social disruption, including an increase in climate refugees across borders." End quote. In 2015, roughly 34 million people were affected by extreme coastal flooding. Without mitigation, this number will rise to 246 million people by 2100. As a point of comparison, that is roughly the equivalent of 75% of the U.S. population. With proper mitigation, this research predicts that number could be brought down to 119 million people, which is still terrible, but it's better. And I guess better is better than nothing. Okay, Earth may be a planet, but I'm ready to look at other parts of our cosmos. After a break, we're going to look at all the most beautiful science of the past week, and the universe does not disappoint. Stay tuned. This past week, we saw the 10th anniversary of a meteor exploding during morning rush hour traffic over the Russian city of Chelyabinsk. Here in the U.S., that event occurred in the final hours of Valentine's Day, and astronomers the nation over took to their phones to watch all the dashcam videos as we demonstrated once again that asteroids can distract us from anything. As if in celebration of that event, on February 12th, a 1-meter-across meteor struck Earth's atmosphere over northern France. Initially discovered by Hungarian meteor hunter Christian Czarnecki, this object led to my favorite tweet of the year. From the European Space Agency Operations Twitter feed, we have a 1-meter meteoroid, small asteroid, has been detected and is expected to safely strike Earth's atmosphere over northern France between 3:50 and 4:03 Central European Time. In the area, look out for a shooting star. That meteor's path brightly illuminated the skies over England and France. Analysis of the seemingly countless phone videos narrowed the search zone for possible meteors to a rural area of France, and as of the recording of this show, teams have begun to find their own pieces of this space rock, but details are still scarce. When we know more, we'll bring it to you right here on EVSN. In our lifetimes, there have been, I am very grateful to say, no major impacts on the surface of our planet. What we know about impacts comes from exploring inside craters here on Earth and on the Moon and Mars, and from imaging craters on pretty much every surface in the solar system. One of the prettier discoveries was the presence of glasses where quartz-rich sand is impacted. The glasses have an amazing crisscrossed lamellae structure that are clearly visible in X-ray microscopy. While we know these glasses are formed in impacts, the details of how they form have been missing until now. At the German electron synchrotron DESI, researchers smushed quartz grains between two diamond anvils to simulate the forces experienced during an impact. This was done while imaging the quartz structure. According to lead author Christoph Ottsen, the team observed that at a pressure of about 180,000 atmospheres, the quartz structure suddenly transformed into a more tightly packed transition structure, which we call rosite-like. The higher the pressure rises, the larger the ratio of silica with a rosite-like structure in the sample. But when the pressure drops again, the rosite-like laminae do not transform back into the original quartz structure, but collapse into a glass lamellae with a disordered structure. End quote. This final structure is exactly what we see in nature at much larger scales. Who says science isn't a high-pressure environment? Apparently, some of the coolest results are literally shaped by diamond. One of the constants of our solar system is the presence of rocks just about everywhere. And currently, none of them are predicted to hit the Earth, and that is good. What is less good is knowing the majority of small space rocks are still waiting to be discovered. Getting in on the asteroid hunting game is the JWST. During its calibration period, JWST's mid-infrared instrument quite accidentally imaged a previously unknown asteroid that appears to be 100 to 200 meters in size and is located on the inner edge of the main asteroid belt. Essentially, the JWST spotted something the size of the Roman Colosseum out beyond Mars. Researchers are now realizing that tiny asteroids, which exist in unknown numbers, may be a common feature in JWST images of objects viewed through the disk of the solar system. It looks like JWST is now a rock hunter. While JWST appears to like rock hunting, it was designed with more far-out tasks in mind. Working hand in hand with gravity, JWST has allowed researchers to directly image star formation in bright clumps and galaxies at the beginning of the universe. Here is what we're seeing. Between 680 million years and 5 billion years after the universe began, light left 18 different galaxies and started flying through the universe. Along the way, the gravity of a massive galaxy cluster helped focus more of that light toward us than we'd otherwise see. That light, after traveling for billions and billions of years, was observed by the JWST several months ago, and researchers have been working to understand what's going on ever since. These observations allow researchers for the very first time to see in detail how star formation starts in galaxies. The clumps they identify range from less than 40 to hundreds of light years across and have masses ranging from 100,000 to a billion solar masses. Some of the clumps overlap in size with star clusters we see in the modern universe. They do find, however, that the galaxies seen from the earliest times in our universe have higher densities than modern star clusters. They also find the ages and sizes of some of these clusters are consistent with them being the early stages of what we see as globular clusters today. This is just one study of 18 galaxies seen through one galaxy cluster. Over time, these kinds of observations are going to allow us to see how galaxies formed and how star formation lit up galactic disks and filled the outskirts of galaxies with star clusters. We are, in many ways, building a film of the life of a typical galaxy by observing as many galaxies as we can across all of time. And it is beautiful to see. Every time astronomers get a new telescope, there is a flurry of, and Telescope X sees the oldest, faintest, smallest, youngest thingamabob for the very first time. Right now, we are experiencing peak JWST firsts. Next year, we'll be seeing, I hope, everything the Rubin Observatory has to offer, and someday after that, it will be the Roman Space Telescope. For now, peak JWST. In another beautiful first, JWST has identified the source of infrared light in a merging galaxy system. Prior to these images, researchers knew that this system, 2Zwicky 096, appeared to be a merger of galaxies, and that a powerful source of light lurked embedded in cosmic dust. With JWST's infrared abilities, it can see longer wavelengths of light that pass unhindered through the dust. The brightest source they see is no larger than 570 light years across, and if its light comes from star formation, they estimate it is forming 40 to 60 solar masses of stars a year. This powerful source of energy isn't anywhere near the core of either the galaxies known to be merging, and it is accompanied by 11 other star-forming sources, of which 5 were previously unknown. A paper in the astrophysical journal Letters, led by Hane Anami, suggests this light may come from the shredded remains of a third galaxy. Future planned JEDBOST results should clarify exactly what is going on. Now, before we go to break, I have one more story. In what seems to be becoming a weekly segment, I have yet another new paper on yet another possible way to explain dark energy, that thing that is expanding our universe apart at an accelerating rate. Appearing in a pair of papers led by Duncan Farrar, this work is free of particle physics and instead looks for dark energy in the physics of black holes. And these aren't theory papers making observational predictions. These are observation papers that realized they matched an existing theory. This team looked at supermassive black holes in the centers of massive elliptical galaxies. These systems formed early in the universe and then stagnated. And while I fully expect that a galaxy left alone in the universe generally shouldn't change that much, the universe had something else in mind. Somehow, between nearly 9 billion years ago and now, the supermassive black holes in otherwise dormant galaxies grew. To paraphrase their paper, they expected negligible change between galaxies in the local universe and the distant universe. But supermassive black holes somehow grew by a factor of 20. A factor of 20. This discovery is actually predicted by relativity if black holes contain vacuum energy and are coupled to the size of the universe. In a paper published in 2019, K.S. Crocker and J.L. Viner derived a formalization for the equation describing the expansion of the universe, the Friedmann cosmology, that considers how compact objects contribute as pressure sources. When the first generation of stars died, the most massive stars formed the first population of black holes. And in this theory, their internal pressures fundamentally changed the universe, adding in a new pressure that would remain constant over time. As described in the new papers by Farrar and collaborators, black holes are thus coupled to the universe. And as the universe grows, so do black holes grow. The 2019 paper said that the cosmological coupling of black holes should have a value of 3 if their theory is correct. We're not going to go into how they found the value 3. It's the value 3. Continuing on. And in the new papers, Farrar's team observationally determined that K value is 3.11 plus or minus about 1. While the error bars on this are a lot higher than I'd like, their data is compelling. They combine data from multiple telescopes and multiple surveys and consistently got the same within error bars results. These results also rule out our traditional way of looking at black holes. No matter what else we learn, this work seems to show that when left alone, black holes will grow, which is weird, as is everything about relativity. I generally like relativity. Buried in this work is a tantalizing prediction. Old stellar mass black holes that formed from the first stars should still be around, but now they should be more than 100 solar masses in size. These objects, if they are out there in the outskirts of galaxies, could be the massive compact halo objects or machos that are sought for as a component of dark matter. This has potential effects on what kinds of gravitational waves we'll see from merging black holes and what we may see in terms of gravitationally lensed gamma ray bursts, growth rates of quasars in the early universe, and many other observable factors. And this theory for dark energy requires no new physics. explains how dark energy can appear after the rest of the universe has settled into existence and stars have started to form, and it clears up weird observations about otherwise boring galaxies. And more observations are needed, a lot more observations. But so far, there is nothing to rule out this theory. And I have one more line of physics I need to keep track of. And keeping track of dark energy is way more interesting than climate change. Up next, we take a look at all the ways, or at least many of the ways, AI is starting to aid in modern astronomy. Stay tuned. Earlier in this show, I mentioned in passing that if all goes well, next year will be the year of firsts for the Rubin telescope. Known as the LSST for decades, this telescope has a mirror just over 8 meters in size, and it will host the most advanced camera system on the planet. With 3.2 gigapixels per image and plans to image the entire visible sky every few nights. Rubin will record 1.28 petabytes of data a year, and it is designed to discover myriad asteroids, icy objects, and transient phenomena that come and go from our sky. This is more data than humans can process. Frankly, writing software that can process this data for us has become an imperative in astronomy. And this is where we need AI. The goal is simple. Rubin takes a suite of images and all the known objects are labeled and then checked for changes. Then software looks at all the newly observed objects and says, yes, this one is moving in a way that is consistent with this being a Trojan asteroid out near Jupiter. Or, yes, this one is shaped like a spiral galaxy, but it was too faint to see in earlier surveys. Then the smart software should work to both alert astronomers to objects it can't make sense of, and it should work to try and find patterns in the things it can't make sense of. This requires a combination of algorithms. We need what are called supervised machine learning algorithms that are fed training data that teaches the software, this is a spiral galaxy, this is an irregular galaxy, and so on, so that the software sees in the data specific patterns astronomers know to look for. This could be literal patterns, as in the shape of a galaxy, or patterns in how the brightness of a star changes when a planet passes in front of it, or patterns in an object's motion as it goes through the sky. The other kind of algorithm we use is called an unsupervised algorithm. In this case, software is told, look at these characteristics of a thing and see what patterns you can find. And honestly, software can sometimes find subtle patterns that defy our human skills. In the lead up to the Rubin Observatory seeing first light and beginning its data flooding survey of the sky, researchers are developing algorithms and running them against other data sets to see what we can learn and to see what computers can learn. One of the best examples of AI use in astronomy is the search for exoplanets. AI can find both forming planets and planets in mature systems, with the latter being a bit easier, as planets orbit distant stars. Geometry sometimes works in our favor and allows us to see the star's light dim ever so slightly as a planet orbits in front of it. A variety of different spacecraft are designed to look for these planetary transits, with the TESS mission being NASA's flagship planet finder. Launched in 2018, this mission returns image after image of different patches of the sky that it cycles through. Some of the stars in the fields will be in multi-star systems that cause us to see varying stellar brightnesses. Some of the stars will be variable stars that intrinsically change in size and luminosity over time. Sorting the tiny variations of planets out of everything else that is going on is tedious work. And in 2020, an algorithm written by Warwick University researchers demonstrated that it can take on that job, with 50 new planets being found in its first run through the data. Programming software to do tedious things is a real brain saver for scientists. We want computers to take over these kinds of tasks so that we can focus on what science can be learned. Sometimes, though, we need computers to do more than save us from the tedium. Sometimes we need them to do things we can't do with our eyes and minds consistently well. And this is where machine learning is now being used to find forming planets in messy star-forming disks. As forming planets orbit, they will create tiny wiggle shapes in surrounding material with their gravity and motion. Finding this feature can be hard for humans. And as University of Georgia researcher Jason Thierry puts it, quote, "In a sense, we've sort of just made a better person. To a large extent, the way we analyze this data is you have dozens, hundreds of images for a specific disk, and you just look through and ask, is that a wiggle? Then run a dozen simulations to see if that's a wiggle. And it's easy to overlook them. They're really tiny, and it depends on the cleaning. And so this method, using AI, its accuracy gets planets that humans would miss." Code developed by Jason and his team is now actively searching for baby planets in data from the ALMA telescope. And this, once again, means more science people can do. And in this case, humans can hand off to computers the challenge of finding planets, which is really something computers do better. And some tasks are both hard and tedious, and potentially can yield amazing results. And these are tasks we really want computers to do for us. And one of those tasks is literally looking for aliens. Note, we have not yet found aliens. Neither humans nor machine learning algorithms have found aliens. They have found synthetic signals added to the data to test things, but not aliens. Okay, just so we're clear, I would tell you if we had found aliens, and we haven't. Carrying on. The SETI Institute utilizes radio telescope data collected for research to also look for possible radio signals from alien civilizations. As the number of radio telescopes increases, there is more and more data to process. According to Peter Ma, quote, "In total, we had searched through 150 terabytes of data of 820 nearby stars on a dataset that had previously been searched through in 2017 by classical techniques, but labeled as devoid of interesting signals. We've scaled this search effort to 1 million stars today with the Meerkat telescope and beyond. We believe that work like this will help accelerate the rate we're able to make discoveries in our grand effort to answer the question, are we alone in the universe?" End quote. Ma led a team of researchers in the development of a new algorithm developed as part of the Breakthrough Listen project. A description of this work is published in Nature Astronomy and talks about a reanalysis of data from the Green Bank telescope. The algorithm successfully flagged data that had specific characteristics typical of artificial signals, including being in a narrow band of radio frequencies, being localized in position, and shifting in frequency in ways that match the Earth and the receiver's motions. The signals detected so far are not little green men. They are instead the kinds of naturally occurring stuff that gets us excited and then either teaches us new physics or they are signals that we only see once and can't conclude anything about. Knowing that no signal will get missed, however, means we can get back on target to look again a little bit faster, and maybe, just maybe, we can find more new physics, or perhaps somehow detect another world's version of I Love Lucy. At the root of all artificial intelligence algorithms is pattern matching. Humans are really good at pattern matching, but we'll also imagine the face of Stalin on a shower curtain and see eyeballs in poached eggs. And don't forget that famous face we all saw on Mars. Humans are good at finding simple patterns like faces, and we'll find them even where they aren't, just like a face swap app gone mad. And when it comes to finding complex patterns, it turns out we still find things that aren't there thanks to psychological issues like confirmation bias. And we miss patterns that require too many variables to be considered. Terrestrial weather predictions require software models, and predicting space weather is a good job for AI. Northumbria University physicist Andy Smith is one of the folks working on this task, and he explains, quote, "The technology we are developing through this project could protect the Earth from the impact of geomagnetic storms, as we could predict when such events would occur, allowing us to prepare. For example, in the UK, this would be coordinated through the Met Office, which would inform the national grid, which would in turn activate plans to protect our power grid. It's not a case of the Earth will be hit by a serious space event. It's a case of when. And this physics-inspired artificial intelligence system will allow us to predict such an event and protect ourselves from it." End quote. And Smith and his team are actively generating this AI that will make the predictions we need. Software that can learn the way humans can learn is coming. Some would even say it's already here. Software is capable of reviewing more data and finding more complex relationships and patterns than humans. Software, however, can't as easily say, "Oh, that's a mistake." ChatGPT falls victim to fake news and parody information. Software can't use a gut feeling to guess at when it needs to double fact-check information in Wikipedia or make sure that a posted image of SpaceX's latest test isn't just someone's data visualization. For now, the more AI software sees how humans classify data, the more it's going to learn patterns. It is still inexact. There are famous issues of software deciding the best way to distinguish between wolves and dogs was to check the images for snow. Still, when we are consistent in our behavior, software can learn to do what we do when the tasks are recurring. Where humans for now are unique is in our ability to say, let's look at the physics, the chemistry, the root science underlaying everything the software is labeling, and let's figure out from first principles how all of this works. Computers can say, this is a trend. But we remain the one thing that can answer, why is that happening? And when that changes, that is something I leave for science fiction writers to address. After the break, we're going to have on aerospace correspondent Eric Mattis to talk about this week's launches and talk about the troubled Russian capsule cooling systems. Stay tuned. Not all tech is smart. And honestly, there are certain technologies that don't need to be smart. My hot water kettle. It just needs to make water hot at the press of a button. I'm sure there are AI-driven electric kettles out there somewhere. But for now, I can't think of a reason to have one. And as much as I love my smart lights and digital home companions, it will be a while before our AI algorithms make their way to space. For now, the ISS and other missions rely on a much more hard-coded set of rules that are tried, tested, and known to work. And even on the ground, it is sometimes easier to brute force our way to an answer instead of training software to learn. For instance, software developed at the University of Connecticut for processing Landsat images of Earth can now remove the clouds. To be clear, the software can't do some kind of Photoshop magic to remove clouds from any single image of the Earth. Instead, the software looks at sets of images taken over a short period of time, and it can identify the cloud-free parts of the images and stick all the different pieces together to get a single composite image. Unlike consumer software that allows human-free images of city streets to be generated by looking for things that move, this software specifically identifies bright features, like clouds or snow, that usually aren't there and excludes those regions. The software is still capable of identifying where actual changes, such as logging or construction, have taken place. It's estimated that 60% of satellite images of Earth contain clouds. This nifty tool will liberate scientists from having to find the 1 or 2 images in a data set where the place they want to study is actually cloud-free. It will allow farmers to get a complete perspective on their crops, forestry workers to assess fire damage, and overall changes in coastlines and city sprawl to be documented. No AI required. One super annoying facet of Earth science is we can't really escape clouds. With astronomy, we can just put things in orbit. With Earth science, even low-flying drones can be thwarted by fog. There are days I'm really glad my science is above the weather, and space telescopes are an option. Before we put anything in orbit, companies and government agencies do their best to make sure their technology is certain to work. On February 6, NASA released funky-looking images of the high-gain antenna for the future Roman Space Telescope, which is named after researcher Nancy Grace Roman. This antenna will transmit at 500 megabytes per second, which is the highest data transfer rate of any NASA astrophysics mission so far. While this may seem slow compared to high-end home internet, this mission has to accomplish a lot more than your Wi-Fi router. The antenna has to survive temperatures ranging from -32 to 140 degrees Celsius. And instead of sharing data across your house, it has to send it 1.5 million kilometers from L2 to its receivers in New Mexico. Getting that much data across that kind of a distance is pretty awesome. And the Roman Space Telescope will do it with a 5-foot 6-inch diameter carbon composite dish. Now we just need to see more parts of Roman making their way into final testing and integration. This mission is meant to launch in or before March 2027. While I wait for Roman to launch, other spacecraft are getting their days to shine, or fail. And this, I couldn't even keep track of what all happened. And I'm grateful to welcome aerospace correspondent Eric Mattis on to talk launches. Hey, Eric.
Hey, Pamela. This week has been a wild one, with breaking news coming in right up to our recording time. First up in this week's Rockets update is more news on the troubles with Russian spacecraft docked to the space station. As you may remember from this past December, the Soyuz MS-22 spacecraft sprung a leak in its primary exterior cooling loop, right before 2 cosmonauts were about to perform a spacewalk on the Russian side of the station. At the time, Russia stated that the leak was caused by a micrometeoroid, a small piece of orbital debris in orbit near the station. Because of that, Soyuz MS-22 was declared unfit for crew return, and the next Soyuz to go up, Soyuz MS-23, was reassigned to launch uncrewed and bring them back to Earth. Russia has launched a Soyuz for this purpose before, but not for several decades. The crew of Soyuz MS-22 would return at the end of Soyuz MS-23's nominal mission, spending about a year in space. This past week, another Russian spacecraft at the station, Progress MS-21, suffered an almost identical cooling loop failure, Roscosmos briefly considered delaying the launch of Soyuz MS-23 to investigate the issue, but were reluctant to do so because the vehicle was already filled with its propellant. The propellant is so corrosive that once it touches the tank, it cannot be drained or refilled later. So, for better or worse, Soyuz MS-23 will launch uncrewed into space no earlier than the week of February 20th. And Roscosmos reported on their official telegram that the spacecraft had been inspected and, quote, no maliciously drilled holes were found, unquote. The almost identical failure of two similar cooling loops 3 months apart calls into question Russia's explanation for the failure of Soyuz MS-21's radiator, namely that it was caused by a micrometeoroid. While lightning often hits the same place twice, micrometeoroids less so. Speculation now points to a manufacturing defect. We'll discuss how the retirement of the Apollo generation of engineers are changing the face of spaceflight in a future episode, once Soyuz MS-23 makes it safely to Earth. In more positive news, the Indian Space Research Organization, ISRO, successfully launched their new small satellite launch vehicle. The SSLV is a 4-stage rocket with a solid first or third stages and a liquid propellant fourth stage. Interestingly, the second stage starts up just before the first stage fully cuts off. This is what's known as a hot stage. Hot staging is typically only seen in liquid propellant rockets, which use it to settle the propellant in the bottom of the tank before burning free, instead of using small thrusters dedicated to the purpose. This was the second attempt to launch an SSLV. The first launch of an SSLV ended in failure back in August 2022, when the launch vehicle's guidance computer and accelerometers were overloaded due to shock and separation of the second and third stages. That caused the final stage of the rocket to revert to a backup software program and fire its engine for only 10 seconds instead of the planned 100 seconds. The second flight carried a small satellite built by ISRO to do remote sensing, EOS-7, and 2 CubeSats. One of the CubeSats carried a software-defined satellite built by American company Antares. The other, named AZADisat-2, was built by a team of 750 Indian schoolgirls, organized by a company called Space Kids India. AZADisat-2 was the third satellite made by the group, all of which have been launched on Indian rockets. The purpose of the satellite was to give economically disadvantaged children the experience of building and launching something into space. The 4 payloads on AZADisat-2 included a transmitter programmed with 2 songs, a radiation counter, an expendable structure, and a board with 75 payloads, one from each of the schools that took part in the project. The first AZADisat was lost on the maiden launch of the SSLV, so it's good that they were able to try again. The other launch this week was yet another Starlink. It was successful, delivering 55 satellites into orbit. And now for some statistics for a few of the things that are in orbit around the Earth. There are still 9 toilets in space, 4 on the ISS, 2 on the Tiangong space station, 1 on Shenzhou 14, 1 soon to be burned up on Soyuz MS-22, and 1 on Crew Dragon Freedom. We keep track of orbital launches by launch site, also called spaceport. According to RocketLaunch.live, so far this year, the US has had 12 launches, China 5, Kazakhstan 2, and India, Japan, and the United Kingdom have each had 1. Of these 22 launches, there have been 2 failures, reminding us that space is hard.
Thanks, Eric. I know the MS-23 has been frustrating to cover. As we prepared this show, it went from set to launch this weekend to delayed to March to delayed for an unknown duration. I appreciate you sticking with the news as it happens. As you said, space is hard, and sometimes so is space journalism. But there are a lot of amazing successes to celebrate. One of the more remarkable things that happened was the February 18th, 1930 discovery of planet classic Pluto. What we now know to be misunderstandings in the orbits of outer solar system objects led American businessman turned astronomer Percival Lowell to believe that a giant planet should orbit out beyond Uranus and Neptune. This belief was based on work by William Pickering and his student Elizabeth Williams. This belief drove Lowell to push observers to search for a new planet. While Lowell died in 1916, the search for this ninth planet continued at the observatory he founded in Flagstaff, Arizona. In 1929, Lowell Observatory hired a young man who had taught himself how to build telescopes. That man was Clyde Tombaugh. Using a 13-inch telescope, Clyde Tombaugh took images every few days of the region where Pickering suspected the missing planet should be, and by using a shutter to blink back and forth between the images taken at different times, Tombaugh was able to find a tiny moving light in just the right place. While its apparently tiny size didn't meet with expectations, the world, well, our world, still celebrated the discovery of that world. In 1978, Pluto was discovered to have a companion, Charon, that is half its size. In 2006, Pluto was officially reclassified as a dwarf planet, thus becoming the second object after the asteroid Ceres to have its planet status revoked. In 2015, Pluto was visited by the New Horizons mission, and new results continue to come from that mission's wealth of images. In a paper that came out February 7th, Southwest Research Institute researchers detail how Charon may once have had a subsurface ocean that has now frozen, a process that contributed to the cracking of Charon's surface. Pluto, however, still has a liquid sea beneath its surface. With a 248-ish year orbit, we'll be able to see Pluto where Tombaugh first spotted it in 2178. That's it for now. We're taking next week off for President's Day, but we'll be back with more science and rocketry. Good night, and remember to look up.
Stop and think. How often do you take the time to set goals? And when you set those goals, how often do you hit them? The problem is the word goal setting. We all have goals, but goals are just wishes. Goals are what we want. What we really need is called result setting. My name is Katrin Becker, and what I do is create tailor-made result plans that ensure people will hit their targets. If you are committed for real results, let's chat and see which program is right for you and your team. Goals are just what we want, but together, results are what we will achieve.
As a critical aspect of your operations, you need the right technology partner to provide you and your business the peace of mind of having reliable and efficient IT systems. In addition, with cyber threats, ransomware at an all-time high, adequate, continuous, and proactive data protection for your business is an absolute must. Hi, this is Roland Parker with Impress Computer Solutions. We are experts in tailored IT solutions and professional 24/7 IT support services. We proactively monitor, maintain, manage, and protect your IT and data assets. Additionally, we have the know-how and horsepower to do the correct procuring of any and all computer systems or software your company may need. Having the correct IT infrastructure and not being able to operate safely and correctly is very expensive and can eventually destroy growth. So take a decisive step and call me today for a complimentary consultation at 281-647-9977 for your unique IT needs.
bookkeeping team is key to any successful business. At Gunderson's Bookkeeping, our passion is to help small business owners grow, be profitable, and to prosper. We specialize in supporting small to mid-sized business owners who want to hire a full-time or even a part-time bookkeeper, but just do not have the funds. In addition, we free business owners from the tedious tasks of bookkeeping and help them focus on their business operations, their growth, and profitability. Gunderson's Bookkeeping is your business solutions partner offering a broad range of services to meet the needs of our clients. A profitable business needs accurate and reliable books, so take a strong step and call us today for your personal, no-risk consultation.